Effect of concentration of Al2O3 nanoparticles in base fluid on thermal and flow properties to enhance the heat transfer rate. Abstract cooling is almost important in industry. It is needed to improve the performance of cooling system. However, due to the low thermal conductivity of fluid, there will be limitations for the heat transfer characteristics. Nanofluid I.E. suspension of nano-size particles in the base fluid such as water, ethylene glycol oil, and diesel were used as innovative heat transfer fluid for cooling applications because thermal conductivity of the nanofluid is more than the conventional fluids such as water, ethylene glycol oil, etc. There are many literature surveys available which shows that increase in the thermal conductivity and heat transfer characteristic with increased in concentration of nanoparticles in base fluid. The aim of this review is to summarize how increased concentration of nanoparticles increases the thermal conductivity and heat transfer rate. Also about the effect on the thermal and flow properties of nanofluid. Keywords: nanofluid, Al2O3, concentration, thermal conductivity, heat transfer rate. Introduction. Conventional fluids such as water, engine oil, ethylene glycol was used as heat transfer fluid. These fluid having low heat transfer characteristics and affects the performance of the cooling devices like heat exchangers and in many electronics equipments. There are many researchers going to enhance the heat transfer rate to enhance the efficiency the devices. Hence many authors used the solid particles in size mm in water, engine oil, and ethylene glycol to enhance the thermal conductivity and heat transfer characteristics of the fluid. But due to the addition of the size particles in water/engine oil/ethylene glycol, sedimentation problems occurs and resulting in the viscosity of the fluid increases. The thermal conductivity of the solid particles are more as compared to the base fluids such as water/engine oil/ethylene glycol, etc. Suspension of nano-size metal particles in conventional fluid called as nanofluid increases the heat transfer characteristics of the nanofluid and thermal conductivity. Use of nano-size metal particles in water, oil, and ethylene glycol which enhance the thermal conductivity and heat transfer characteristic can be used for many engineering heat transfer applications. Nanofluids are suspended nano-size particles in the base fluid. The size of the nanoparticles vary from 1 to 100 nm. Nanofluids are not simple liquid-solid mixture. Nanoparticles which are used to mix in liquid should not react with base fluids and stable for long duration in order to enhance the thermal conductivity and heat transfer characteristics. Nanofluids have attracted great interest recently because of enhanced thermal conductivity and heat transfer rate 2 to 6. This article aims to an overview of the concept of alumina-based nanofluids and detailed research about Al2O3 water carried out around the world. In this article we discuss the parameters such as thermal conductivity, specific heat, viscosity, and temperature of Al2O3 water-based nanofluid. Also discussed preparation methods of nanofluids. Thermal conductivity. Thermal conductivity is an important property to increase the heat transfer rate of base fluid. Thermal conductivity of the solid particle, metals, higher than that of the base fluid. Hence thermal conductivity of the suspended particle in the base fluid increases the heat transfer performance. There are different methods used to identify the thermal conductivity of the nanofluids. Temperature oscillation method. Steady-state parallel plate method. Transient hot wire method. The transient hot wire method is extensively used to measure the thermal conductivity of nanofluid, which is explained in the literature survey 5. Preparation of nanofluid. Single-step direct evaporation method. Two-step method. Thermal conductivity measurement techniques. Temperature oscillation method 9 to 12. Steady-state parallel plate method 8. Transient hot wire method 1 to 5. Experimental result on thermal conductivity of Al2O3 based nanofluids. Generally, thermal conductivity of nanofluids increases with increasing volume fraction of nanoparticles with decreasing particle size. Shape of the particles also influences the thermal conductivity of the nanofluid. Thermal conductivity of the nanofluid increases with in temperature of base fluid. Brownian motion of the particle, Interfacial layer with additives. 3. Effect of volume fraction of nanoparticles on thermal conductivity of Al2O3 based nanofluid. Volume concentration mostly less than the 5% in all the cases. From all the paper, the maximum thermal conductivity observed for 4% to 5% volume load. In case of water-based nanofluid, which increases 30% to 32% increase of thermal conductivity and 30% increase in thermal conductivity in case of ethylene glycol as base fluid. H1 17 for base fluid as water shows 4% enhancement in thermal conductivity of concentration from 0.3 to 1.0, particle size 48 nm at the enhancement ratio of 1.013 to 1.04. Thermal conductivity enhancement was decreased as concentration increased from 6% to 10%. Sometimes thermal conductivity was increased as concentration increased from 2% to 10% even though particle size almost the same in both cases. Thermal conductivity 2% composition by volume and 21% enhancement in thermal conductivity for 4% composition by volume. Merched 20 reported that larger size particles used also enhance the thermal conductivity using Brownian motion of nanoparticles by the addition of surfactant and application of temperature. The author Merched 20 and Beck 22 also shows that thermal conductivity depends upon the base fluid behavior. Thermal conductivity of nanofluid can be measured by different method, they are temperature oscillation method 9 to 12. Steady state parallel plate method 8. Transient hot wire method 1 to 5. Generally thermal conductivity increases with increase in volume fraction. These methods gives different results for water-based nanofluids. This may be due to the sedimentation and aggregation of nanoparticles, particle diameter, and nanofluid preparation. Steady state parallel plate method seems to be least affected by the particle sedimentation, thickness of the sample fluid less than the 1 mm. But still research has to be carried out which technique is better for different size, shape, volume fraction of nanofluids to enhance the thermal conductivity 1, 7,8, 23. Effect of pH on thermal conductivity of Al2O3 based nanofluid. CS16 conducted experiment for water-based Al2O3 nanofluid for range of 5 to 124 square meters/g using transient hot wire method where he found that pH range was 2 to 11.5 and thermal conductivity of suspension particle is greater than base fluid. The enhanced thermal conductivity increases with increase in the difference between the pH values of aqueous suspension and isoelectric point of the Al2O3 particles. CS16 shows that for 60.4 nm size particles and volumetric composition of 1.8% to 5% thermal conductivity observed was 7% to 21%. Experimental results on viscosity of Al2O3 based nanofluid. Comparing the experimental studies on thermal conductivity of nanofluid, they are limited rheological studies 8. The author 8 shows that for Al2O3 water-based nanofluid and 3% by volume the viscosity increases to 20 to 30% as compared to water. DOS 26 shows that viscosity of nanofluid increases with increase percent volume and that nanofluid considered to be non-Newtonian. As per the study 19 using two-step method Al2O3 based nanofluid for the percentage of to 0.3 without any surfactant at the temperature of 210C to 390C. Viscosity of Al2O3 water nanofluid significantly decreases with increase in temperature and slightly increases with increase in volume fraction. Measured viscosity of Al2O3 water nanofluid nonlinear, occurs at low percentage volume concentration below 2%. As per the author 27 viscosity increases by 83.4% for the volume 5% of Al2O3 water. As per the author when 28 of Al2O3 water nanofluid for the size of 36 nm, 47 nm, and CuO water nanofluid with 29 nm reported that changes in the hysteresis behavior of nanofluid for the percentage volume 1% to 9.4% at temperature 750 C approximately. The water-based Al2O3 nanofluid at 750 C for the size of 36 nm and 4% volume hysteresis behavior of Al2O3 water nanofluid will change on heating and cooling beyond the critical temperature. It is very interesting that hysteresis is predominant only in fluids with higher nanoparticle concentration. The above information from all the researchers shows that change in the relative velocity at lower concentration was minimal over a temperature. As per the author CE24, viscosity of suspended nanoparticles was much larger than the corresponding values predicted by the theoretical one. And also cold 25 enhancement ratios of the viscosity ration of ethylene glycol-based suspension are smaller than those of water-based suspensions, indicating that base fluid is also influenced. As per the cold 25, Al2O3 in engine oil demonstrated that there is transition from Newtonian characteristic to non-Newtonian characteristic, and viscosity increased as is with increase in the percent ration of concentration and decreases with increase in temperature. An optimal layering of is required, perc by volume, in nanofluids so that we can avoid viscosity rise for the application and at the same time increased S's the rise in the thermal conductivity of the nanofluids. So that more studies is required in this direction. 5. Heat transfer characteristic of Al2O3 based nanofluid. Heat transfer aspect of the nanofluid studies by many authors, especially about convection and multiphase heat transfer of nanofluid, more critical. Author Pak and Cho 30 and Putra 31 studies the natural convection using Al2O3 and TiO2WITH water as base fluid and found that Nusselt number of nanofluid increases with increased concentration and Reynolds number, and an apparently paradoxical behavior of heat transfer of nanofluid observed. I.E. heat transfer deterioration was observed in the experimental study. That is due to the followings: means depends upon the parameters such as particle concentration, materials of particles, geometry of the containing cavity. Harris 32 discussed QA water and Al2O3 water in a cylinder at constant wall temperature increasing the concentration, laminar flow convective heat transfer. He found that at low concentration heat transfer characteristic of both QA water and Al2O3 water are same and close to each other. But increase in the concentration shows that heat transfer ration of the nanofluid to homogeneous moduli of Al2O3 water increases. Author 33 also studies the laminar flow with forced convection heat transfer of Al2O3 water inside circular tube with constant wall temperature and measured the following numbers: Nusselt number, Peclet number, Reynolds number. And the result observed was enhancement of heat transfer characteristic of Al2O3 nanofluid with increase in concentration. The author 34 shows that in his experiment for Al2O3 and ZrO2 water-based nanofluid for turbulent convective heat transfer for various flow ratios I.E. Reynolds number 9000 Re 63000. The authors compare the experimental data to prediction made using the traditional single-phase convection heat transfer and viscous pressure loss correction for fully developed turbulent flow Dittus-Boelter and Blasius-Max/Adams respectively. The author in his investigation shows that the calculation of Reynolds number, Nusselt number, and Prandtl number in terms of measured temperature, loading-dependent thermal conductivity and viscosity of the nanofluid. Therefore, no abnormal heat transfer enhancement was observed in this study. Xian and Li 35 conducted an experiment of Al2O3 water-based nanofluid in cylinder, tube, to investigate convection heat transfer and flow features. They measured heat transfer coefficient and friction factor. They discussed effect of volume fraction of suspended nanoparticles and Reynolds number on the heat transfer and flow features. Wen and Ding 24 conducted an experiment of Al2O3 water, deionized water, in copper tube of laminar flow and showed enhancement in convective heat transfer of nanofluid in laminar flow. Enhancement was particularly significant in the entrance region. The reason is that for enhancement are migration of nanoparticle and resulting disturbance of the boundary. UET Al36 conducted experiment for Al2O3 water nanofluids and measured the CHF, critical heat flux. Further investigated that the critical heat flux of nanofluid increased 3-fold times that of pure water. This is an unprecedented phenomenon. although in his experiment shows that average size of the bubbles increased and bubble frequency decreased significantly as compared to pure water. Bang et al. 37 studies boiling heat transfer characteristic and pool boiling heat transfer phenomenon for Al2O3 water nanofluids and compare result with pure water. The author shows that poor heat transfer performance of nanofluid in boiling heat transfer due to the deposition of nanoparticles on the surface of plate both in horizontal and vertical pool boiling. Surface characteristic will change due to the deposition of nanoparticles, hence CHF has increases. Das et al. 38 studies boiling, pool boiling, in water Al2O3 nanofluids in horizontal tube of small diameter and shows that deterioration of heat transfer is less in small narrow tubes as compared to large industrial application tubes, which makes less susceptible to local overheating in convective application. Farajalahi et al. 39 studied the water Al2O3 and TO3/water nanofluid in shell and tube heat exchanger with turbulent flow and shows that at optimum concentration of nanoparticles in water TO3/water nanofluid having better heat transfer characteristic than Al2O3/water based nanofluid and optimum concentration of nanoparticles in water exist. Author also shows that the heat transfer characteristic of Al2O3/water nanofluid increases with increased concentration. Author 40 studies that alumina-based nanofluids used in oscillated heat pipes and shows that better heat transfer rate at 0.9% weight. This is an optimal mass fraction to get maximum heat transfer rate in oscillate heat pipe, and it decreases thermal resistance 0.14 C/W when power input was 58.8 W at 70% filling ratio and 0.9% mass fraction. Author shows that settlement of nanoparticles take place mainly at evaporator. If change the surface condition at the evaporator which increases the heat transfer heat. Ho et al. 41 conducted experiment for different size closed enclosure, vertical. The solid loading of 0.1% to 4% for the Rayleigh number 6.21A103 to 2.56A108, the average heat transfer rate for 3 enclosures is constant with assessment based on the changes in thermophysical properties of nanofluid formulated. Author shows that there will be systematic degradation of heat transfer for volumetric percent increases greater than 2% over the entire range of Rayleigh number. Nanofluid contains 0.1% volume, heat transfer rate increased to 18% compared with that of pure water in largest enclosure for high Rayleigh number. The enhancement in the heat transfer rate is not only due to changes in thermophysical properties of nanofluid but also other properties. Nayak et al. 42 demonstrated experimentally with Al2O3 water-based nanofluid instability is suppressed and flow rate decreases as compared to water natural flow rate. The flow instability occurs only in water. The addition of nanoparticles in water suppress the instability and increases the natural circulation of flow rate. Heat transfer studies of Al2O3 water-based nanofluid very important. Heat transfer rate increases with increase in volumetric concentration. Cost and stability duration of nanofluid is also dependent for the application. 6. Application of alumina-based nanofluids. As per author Kulkarni et al. 46, Al2O3 nanofluid used as a coolant electric generator and also found that the efficiency of waste heat recovery increases for nanofluid due to its superior convective heat transfer coefficient. As per Wu et al. 47 observed as potential of Al2O3 water nanofluid as a new phase change material for thermal energy storing of cooling system, it reduces the total freezing time 20.5%. Infrared imaging photographs suggest that the freezing rate of nanofluid is enhanced and by only adding 0.2 Wt% Al2O3 water. Used to cool the transformer, it is useful in Navy as well industry, power generation industry, to reduce the size and weight of transformer. It is important because in ever-growing demand for greater electricity production necessitates to upgrade transformer on Al2O3. Water/oil can be used. Large scale and at the high cost. It can replace the conventional transformer oil with to cool automobile engine, welding equipment. High heat flux devices such as power micro tubes and high power laser diode arrays. Al2O3 water nanofluid could flow through tiny passages in MEMS to improve its efficiency. Use of nanofluid increases, CHF, critical heat fluxes in forced convection, hence it is used in nuclear applications. As per the author 43 studies, if nanofluid improves the chiller efficiency by 1%, saving of 320 billion kWh of electricity or an equivalent of 5.5 million barrels of oil per year. Used in deep drilling applications. For increasing the dielectric strength and life of transformer oil by dispersing nanoparticles. When Al2O3 experimentally investigated use of nanofluid, Al2O3, for cooling microprocessor or other electronics equipments in closed loop. Used to enhance the consider heat transfer and cooling of cooling block convective heat transfer coefficient considering turbulent flow. As per the research, use of 6.8% by volume nanoparticles heat transfer coefficient about 40% increases compared to base fluid and also decreases the temperature of system. Experimentally show by U et al. 36 for the nanofluid of 36 nm 47 nm, 36 nm size is most efficient heat transfer rate than 47 nm. Experimentally show by U et al. 36 shows CHF for pool boiling from a flat square heater immersed in Al2O3 water-based nanofluid in a concentrating range 0 to 0.05 G/L, CHF drastically increases than in pure water, which is raising the chip power in electronic components and cooling requirements for space applications. Al45 dispersed CuO and Al2O3 nanoparticles and anti-foam in engine oil to cool automotive engine for different RPM, it improves heat transfer efficiency and also reduces the temperature of rotary devices. Nanofluid, cost saving, it improves the heat transfer properties of the transformer oil shown in the reference paper. Above all, the application shows that Al2O3 water-based nanofluid having great potential in many applications. However, literature survey shows that application limited to closed-loop application but need more research in open-loop application. 7. Summary. Al2O3 water-based nanofluid can be used in many heat transfer application. Most of the nanofluids which are prepared by ultrasonic vibrator are not stable for long time. Researchers therefore have to concentrate on the preparation of nanofluid which should give consistent result and stable for long time. The thermal conductivity and heat transfer characteristic enhancement of Al2O3 nanofluid are not consistent for many of the researchers, so it may dependent on the surfactant. Optimizing pH. Temperature for different nanofluid. Surface modification. Only few literature surveys available to study the enhancement of thermal conductivity by the nanofluid by modification of size, shape, and surfactant, acidic, basic of Al2O3. But it adverse effect on the heat transfer characteristic of Al2O3 nanofluid. In many literature surveys we observe different degrees of enhancement for the same volume fraction. The techniques which are used for measuring thermal conductivity also alter the values. The effect of temperature on the thermal conductivity of nanofluid at lower concentration up to 400 K was measured but not yet been reported with experiment dealing with the measurement of the thermal conductivity at lower range temperature, but many research has need to be done. Effect of temperature, at lower temperature, on the thermal conductivity. Very few report described the effect of temperature on viscosity at high concentration and hysteresis phenomenon. The researcher has to be concentrating the effect of temperature on nanofluid viscosity at high concentration to study the hysteresis phenomenon, behavior, of nanofluids. Totally review has summarized the basics of nanofluid, its preparation methods and factors affecting the thermal conductivity enhancement in the Al2O3 based nanofluid. It has also identified the areas which require more research for better understanding. The enhancement of thermal conductivity of base fluid will be definite requirement in the future to improve the thermal efficiency of different system.